So, good afternoon, everyone. So, this is Soumen from IIT Kanpur Chemistry Department. So, I'm going to teach you in the organic chemistry some basic principles and techniques. So, in the lecture 7, we have discussed some of the question and answer session of the stereochemistry part, and also some of the which part is already left. And also, if I go quickly with just touching, just by touching somewhere, then 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 we can actually I will discuss some of the things here also. So let's start from today. Question number 5. So question number 4 already I have discussed the relationship between the two groups in the following molecule, cyclohexane molecule, like cyclohexane are also exist in a chair form. This is here I am showing the chair form. Chair form, you can see this is the chair form. Okay, this is the chair form. Then this is the normal cyclohexane form. Then there is something called uh, boat form. So how the boat form looks like? So the boat form looks like in this way. This is also 6 member ring. So this is called boat form. Okay, this is called boat form. Boat form. Okay, now let's say boat form. This is the boat form, and this is the half chair. So there is also one another form. This exists in the stereochemistry. This is called half twist form. This is called twist boat form. Twist boat twist boat form. Okay, so this is the twist boat form. This is the cyclohexane form. Sorry, this is the chair form. This is the boat form. This is the cyclohexane form. Okay, now we'll start from here. So today the question number 5. Question number 5 is they're asking what is the stereochemical relationship between the following two molecules. So these are all can be actually the CH3, and the Cl. Okay. So how you can distinguish what is the stereochemical relationship between the following two molecules? So geometrical isomers are in general how many it is possible. So cis trans, right? Cis, cis and trans, or E and Z, or E and G. Okay, or E and G. And enantiomer, you know that two isomers, stereoisomers should be non-superimposable to each other. So they are also not such this kind of. This is also not. This is not like that the enantiomer is also not possible. And in this case also, actually, if you see, so this is the cyclohexane form. This is the cyclohexane form. This is the actually chair form. So how they see 1 and 3, axial and equatorial. Okay, axial and equatorial is the cis. 1, 3 position, axial and equatorial is the cis. And 1, 3 Cl and this is also one axial. So this is the all the so the dash streamer is also not possible, and these two are also identical. Why it is identical? So you can see this is identical because of the so this is the CH3, and then C hydrogen is here, then one hydrogen is here. Okay, now actually this is not actually if you see the molecule is actually not exactly means properly drawn actually. So if you see that this is the molecule, so if you see, so 1 3 axial, CH3 and CH3. So 1 comma 3, if you see anywhere equatorial and axial, that means this is a trans. Okay, this is a trans. And 1 3 equatorial and axial and axial, that means cis. 1 comma 3 axial and axial, that means this is a cis molecule. Okay, cis molecule. So now if we draw this molecule such a way that where it should be, then the CH3 should be trans, and this CH3 and this CH3 is the axial, this CH3 axial, and compared to this CH3 and this Cl is the equatorial axial. Okay, so then it should be like in this way. So Cl, and here it is a one hydrogen. Okay, now they're asking this Cl. Suppose this is a CH3. Okay, now let's say this is the CH3, and now this CH3 and this CH3 is the same size. Okay, so I'm sorry because of this structure is wrong, because here it is also written CH2 CH3, but actually it is a CH3 and CH3. Okay, so but the answer will be identical. Obviously, anyway, the year will be identical. Okay, now you can see. So the thing is here. So here, this two hydrogen is the above. Okay, it's like a cyclohexane in a molecule, a planar molecule, where the two hydrogen to containing where the CH3 to attack is the above, and the CH3 to CH3 in the below position, and where the Cl also is the top of the plane, and the hydrogen is the below to the plane, means below plane. Okay, so now neither it is a diastereomeric, neither it is an enantiomer, neither it is a geometrical isomer. So one only left. That's why it's called as identical. Okay. Now we'll go to the next question. That is which of the following is an alkane which can exhibit optical activity? Which can exhibit optical activity? Okay. Which of the following is an alkane which can exhibit optical activity? Okay. So now just 1 minute. Oh, hello. हाँ भैया. हेलो. हाँ हाँ हाँ, कोई भी होगा आप उनको दे देना. मैं एक्चुअली मेरा एक क्लास चल रहा है, तो मैं थोड़ा बाहर. हाँ 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 हाँ. ओके ओके ओके, मैं एक बार कॉल कर देता हूँ. एक मिनट. So sorry. So as the question is the which of the following is an alkene which can show the optical activity. So if you see the neopentane and the isopentane, neopentane, isopentane. So first we will draw the neopentane structure. Okay. So first we will draw the neopentane structure. So neopentane structure is how it looks like, and the isopentane. First we'll draw the pentane structure. So you can see any of the structure is the 1, 2, 3, 4, and 5, 6. Okay, it's a neopentane, and the so the if you see the neopentane structure, how it looks like. So first, we'll draw the neopentane structure. So neopentane structure is actually C. Okay, CH3, CH3, then CH3, then CH3. Okay, this is the neopentane. Okay, this is the neopentane structure. Okay, now we'll see the total how many carbon present here. Neopentane structure, and neopentane, so which cannot be show the optical activity, because the carbon which attached to the four different group, then only it can show the optical activity or stereoisomer. Okay, because we know that the if you see the CH3, the carbon four atom is there, four arm is there. So the four arm is not exactly same, because the four arm is exactly same. So that's why it is not possible to show any optical activity, because the first criteria for to show optical activity is the carbon should be high. The carbon should be attached with four different atoms or groups. Then only it can show the optical activity. Even it should optical activity means it will show some value either in the, if you inject this sample in a polarimeter, it will show either in a positive direction or in a negative direction in the rotation. So it depends on the alpha value is the positive or negative, R or S value. But we will not go here. But if you see the isopentane structure, this is the neopentane. This is the neopentane. So neopentane structure is this one. Okay. Now, if we see the neopentane with the isopentane structure difference. So what is the difference between neopentane and isopentane? Whenever you see anywhere the isopentane is there, So that means there will be one at least CH group will be present. Okay, then how it is looks like? Neopentane is the quaternary carbon. Why it is quaternary? Because this carbon, the central carbon, did not have any, the central carbon don't have any central carbon doesn't have any alpha proton, right? Any proton source. Only all the carbons are attached to the different. I mean, all the carbons, all the arms are saturated, satisfied with the other different groups. So now here one hydrogen is there. Now, if you see the isobenzene group CH3, CH2, CH3. If you see the CH2 here and CH3 here, so here one possibility is the, so just because of the, if you change the CH3, if you change the CH3 with the hydrogen and one of the CH3 will replaced by ethyl group, then you will end up in getting the isobenzene group. But still, if you see that this carbon, one group is hydrogen, another group is CH2, CH3, the third group is the methyl, and the fourth group is also methyl. So this is also not possible. Why? Because the four atoms should be, or four groups should be different. Okay, then only it can show the optical activity. Now I'll come to the third point. This is the 3-methyl pentane. Okay, so the 3-methyl pentane is the, so let's say 3-methyl pentane. Okay, now pentane structure is the five pentane means 5 carbon will be there. So now in the 5 carbon, so there will be 3 position, 1 methyl will be there. Okay, methyl means CH3. Okay, now everywhere you just put the hydrogen. Now we'll see the actual structure of this one. So this is the structure of this molecule. Okay, now this is the CH2 and here it is a CH3. Now if you see there, one hydrogen is present here. Now you see, if you pass a plane from here, it is also optically, it is not optically active. Why? Because this group CH2, CH3, this group and a hydrogen. Okay, two group is different. Then another group is methyl. Okay, that is the 3 group is different, but and the 4th atom is also similar to that of the first one. So that means this is also not possible. This is also not optically active. This is also not optically active, and the first one, neopentane, also not optically active. Now the question is the 3-methyl hexane. So now we'll first draw the 6 carbon, because this is a hexane, right? So total it will be 6 carbon. So 1, 2, and 3, and it is a 4, and it is a 5. Okay, 5. 1, 2, 3, 4, 5, and 1 will be 6. Okay, so now we'll put the 3-methyl. 3 position will be 1 methyl, and here will be on CH3 group. Okay, now the question is the 3 position methyl is there. Now we have another proton is here. Okay, now we have one proton is also there. So now what we have to do is the so the one carbon chain is the CH2, CH3, and the second one is the methyl group. Third one is the hydrogen, and the fourth one is the CH2, CH2, CH3. So that means it is also actually what are the criteria for the optical activity? One compound can, how the compound will show the optical activity. It can match with the what are the criteria for the optical activity. So now if we see the molecule, now if we arrange, now this is not the 3D way, right? This is not the 3D structure. If we arrange, if we draw the molecule in a 3D way, so then the structure will be look like here. I have drawn here. So this carbon is a central carbon. So central carbon contain one proton, hydrogen is here. Okay. So now the CH2, CH2, CH3, CH2, CH2, CH3 in the plane. So this is the plane in the plane. Okay. Now the methyl group is there. Let's say methyl group is in the below position. Now the CH2, CH3 is there. This is the above position. Now you can see. So here one possibility. If you inject, if you place a mirror here, you will see the exactly the opposite isomer of the your parent compound. So that that means it can show the optical activity. So let's say, so what will be the configuration of the this molecule and this molecule? Okay, so this molecule and the after mirror images. So this molecule and this molecule. So let's say if we start from the here, let's say, because this is the bulkier molecule. So this is the 1, this is the 2, this is the 3, and this is a 4. Now 1, 2, 3. So let's say 1, 2, 4, or 1, 3, 4. So 2 is the back position. So 1, 3, 4. So this is a clockwise, right? So this is a clockwise 1, 3, 4. So that means 2 is the front. 2 front means negative rule. 2 front means negative rule. And clockwise. Clockwise means we know that the positive 2 back positive rule, clockwise means R. So 2 front negative, clockwise means it will be S, right? So clockwise that means S. So now you just rotate this one, because in the presence of mirror we'll get the different molecule. As you get the different molecule, so as you can see, if you see the molecule, so if you see the this molecule, so here this is also 1, this is also 2, this is 3, and this is 4. Okay, so now the question, now the thing is that if it is 1, then it is 2, then it is 3, and it is a 4. So here the rotation, how the rotation will be. So now the question is, the two front is there. Now the rotation will be different, because if you see if you place the mirror, then it is the anti-clockwise rotation, right? Now the clockwise rotation, front negative rule, clockwise means R, anti-clockwise that means it will give the R. So that means these are enantiomer to each other. So this is the R molecule and this is a S molecule, right? Now we actually, in one example, we discuss a lot of things here. How the RS configuration, how the one molecule, to how to get the optical activity, and these are the things we have discussed in one question. So now we can see. So this is the question. So that means, so this is also not possible. This is also not show that. This will also not show the optical activity. This will also not show the optical activity. But only this 3-methyl hexane will show the optical activity for this compound. Now we'll go to the next compound. Next question: what is the molecular form for the alkane of the smallest molecular weight, which possesses a stereogenic center? Okay. So now if you see the C4H10, okay, and C7H16, okay. So now the answer is given D. So let's say first draw the C4H10 molecule. So C4H10 molecule is how it is looks like. 1, 2, 3, and 4. Okay. Now C5, 1, 2, 3, 4, and then 5. Okay. Possesses stereogenic center. Okay. Now C6H14. So you can see H10 mean H10 only possible CH3, 6 and 14. Here it is 5 and 12. Okay, 5 and 12. 5 and 12. So now you can see 5 and it is a 5, 6, and here it is also 6. So this is also 12, and here also same. Here also same, but in the case of C7, answer is given C7H16. 1, 2, 3, 4, 5, 7. Okay. So now here the one problem is the question is not actually clear actually. So they are asking, that why the molecule is not, why which molecule possesses, smallest molecule possesses a little bit the stereogenic center. Okay, but I think this question we can discuss in later. We can discuss, maybe. I don't know. Maybe this question has some doubt. So what is maybe something missing here? I think, yeah. Alkane of the which of the molecular formula for the alkane of smallest molecular weight which possesses a stereogenic center? Okay, maybe we'll discuss later. We can discuss. So we'll skip this question at this moment. Then, but C6 is how it is. 6 is look like C, and C. Three carbon bond is there. Then 4, 5, and now it is just 6. This is CH3. Okay, and here also CH3 is there. Now you can see a stereogenic center, which causes a stereogenic center. Stereogenic center only possible if there is a possibility of the chiral center. Chiral center means chiral center where it is possible. So let's say here also it is possible. You see H and but how we can actually see this H12. Okay. Hmm. Okay, we'll discuss this later. Maybe we should not waste time here. We can discuss this one, then we'll go to there. Okay. So here they are asking the which of the following Fisher projections is different from the other three. So maybe the time permit today, I can discuss the what is the Fisher projection, what is Newman projection, and what is the Newman Fisher projection is different from the other three. Okay. So then which of the following Fisher projection is different from the other three? Okay. Now you can see if I discuss it is clearly known. So let's say so this is the you can see here. So oxygen is here. So this is a one. Okay. If we count, this is a one. This is a two. This is a three. Okay. Okay. Now one, two, two, three clockwise, and the four is in the x axis. That means positive rule. So that means clockwise means this is a R. Okay. Now one, two, three, four. Now this is also clockwise. This is will be of R. Now let's say OH and hydrogen is the negative. So one, two, three. Now it is a four. So now you can see one, two, 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 three. Okay. Now it is a actually it is a clockwise. One, two, 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 three clockwise. But actually the thing is that clockwise, but it will be S. Why it is S? Because 1, 2, 2, 3 clockwise, but it is a 4 is in the y axis barabar. Y axis barabar. So that's why it is a negative rule. So that's why it will be S. This is also x axis barabar. 1, 2, 3. So it is going the clockwise direction. So clockwise direction means x axis if the hydrogen if the four atom is with the least priority group in the x axis barabar, then it will be if axis, then if it is in x axis, then it will be a positive rule, that is a R. Here it is also positive rule, but 1, 2, 2, 2, 3, 1, 2, 2, 3 clockwise positive rule R. Here also clockwise 1, 2, 2, 2, 3. Okay, clockwise R, but here it is a S. But in this case, OH 2, 3, and 4. You can see everywhere pH and CH3 is there. pH, so in the first molecule also pH and CH3 is there. Okay, second molecule also pH and CH3 is there. Third molecule also pH CH3 and OH hydrogen pair. pH CH3 pair and OH hydrogen pair. They will be in the same axis. They should be in a same axis. But here the fourth example, pH is the pairing with OH, and where the CH3 is paired with hydrogen. So that's why it is different. Okay. So that's why the answer will be D. But first of all, I would like to show you how the Fisher projection in this manner, how you can actually identify, how you can find the RS configuration. So let's say first we'll go to the one simple example. Okay. So A, and it is a B, C, and D. Now priority order. Now we'll discuss the priority order. Okay. What is the priority order? The priority order will be A, B, E, then is D. Okay. Priority order. Now If this is y-axis, right? This is y-axis, and this is x-axis that you already learned in uh, uh, 12 means in mathematics class. Okay, so here I will not go details about why it is x-axis, why it is horizontal, vertical. This is called actually horizontal, and this is vertical. Y-axis is called as a vertical, and the x-axis is called the horizontal. So if you see anywhere that the least priority, here least priority is D. If the least priority in the x-axis, if the least priority in the x-axis, so x-axis is the least priority, least priority. Then what will happen? Least priority. Then x, if the x is the least priority, then the positive rule. Then it is the positive rule. If it is a positive rule, that means clockwise is the R and the anti-clockwise is the S. Okay, and the y-axis. If you see the y-axis, if the y-axis barabar, if the least priority present, least priority, then it is a negative rule. It is a negative rule. Okay. Now the clockwise, that means S, anti-clockwise, that means it will show the R. Okay. Now here, now coming to the example. Okay. So this is a one. OH is always one. You know that. And in between CH3 and pH, because pH is the aromatic ring, and due to the Valkyrian nature and the CC double bond, so that's why the pH will be the second position. Third position will be methyl. The fourth one will be the hydrogen. So you can see the fourth priority is in the x-axis. X-axis. So that means so first x-axis positive rule. Okay, now clockwise or anti-clockwise we need to see. So we need to see whether it is a clockwise or anti-clockwise. Okay. Now if you see the clockwise anti-clockwise rule here. Okay. Now if you see the clockwise and anti-clockwise rules here. So 1, 2, 3. That means clockwise and positive rule, that means it will be R. So this molecule is R. Okay. Now here 1 and 2 and 3, 4, and O is hydrogen 4 is also in x-axis barabar. So that means it is also positive rule. Okay. Positive rule. Now 1, 2, 2, 2, 1, 2, 3. 1, 2, 3. That means clockwise. That means this is also R. This will be also R. Okay. Now the third one is the OH is the 1, pH is the 2, and the CH is the 3. So now the 1, 2, 3, 1, 2, 3, and 4 is the in y-axis. So that means if it is in y-axis, then it will follow the negative rule, right? It will follow the negative rule. So if it is a negative rule, then clockwise mean it will be S, anti-clockwise mean it will be R. So let's see, it is a clockwise and anti-clockwise. So first it is a 1, it's just 2, and just 3. Now it is a clockwise rotation. If it is a clockwise rotation, that means I already told you that if it is a clockwise, then it will show definitely negative rule. If it is followed, then it will show the actually it will show the S molecule. So everywhere it is the same, but only in the case of the only in the case of your and only in the case of fourth molecule where the group has been changed. How the in 1, 2, 3 molecule, the pH and CH3 was the paired up, but in the fourth molecule there was a position between the pH and CH3 position was just changed and the replaced by something else. Okay, now we'll go to the other thing. What is the so today's topic, the question, the session is done. Now we'll discuss about the stereoisomer. So what is actually stereoisomer? So stereoisomer is the isomer having the same molecular formula but different spatial arrangements, okay, of their atoms, known as stereoisomer. Okay, so isomers having the same molecular formula but different spatial arrangement of their atoms, known as stereoisomer. Okay, so how it is the maybe the from the definition you are not understanding, because the isomer having the same molecular formula but different spatial arrangement of their atoms and known as the stereoisomer. I'll go to the example. So enantiomer. So what is actually, so we have discussed some of the examples. Some of the example is the enantiomer, diastereomer, and identical isomer. Okay, but we actually never spell out what is enantiomer, how they are looks like, why it is saying that it is the enantiomer. So now the definition is stereoisomer. They are definitely belongs to the enantiomer family, stereoisomer family. Sorry. So, but which are non-superimposable mirror images of each other. Non-superimposable mirror image, not exactly same. Non-superimposable mirror image means not exactly same. If you see the any molecule and the after mirror image, after it put the mirror to that molecule, and if it is showing the exactly same molecule, then it is called, then it is not the enantiomer. Okay, so the stereoisomer which are non-superimposable means it is not superimposed to each other. Okay, non-superimposable mirror images of each other are called enantiomers, and the chirality is the necessary and the sufficient condition for existence of the chirality, or is necessary and sufficient condition for existence of enantiomer. So these always exist as a discrete pairs. How? The two isomers of lactic acid. So lactic acid formula is the CH3CHY Now, if we lactic acid, if we draw the lactic acid in this form, this is called the Fischer projection. Okay, so I'll again and the point out here. So these are all called the Fischer projection. Okay, so that you can recall, you can remember easily. This is called Fischer projection. Fischer. This is called Fischer projection. This is called Fischer projection. So the lactic acid formula is the CH3 CH CH3 CHOH C double OH. So that means it is called the lactic acid. This is actually called the lactic acid. So in exam, if they will ask you to draw the lactic acid formula in Fischer projection, then you have to write in this way. Okay, then you have to write in this manner. So just if you put any mirror images. So let's say this is the lactic acid formula, lactic acid in the mirror images. Now if you put this mirror to this molecule, so now then what you will get is hydrogen will it was initially it was in the right side, but now after putting mirror it will be in the left side. So non-superimposable mirror images of each other. Now you can also numbering the molecule, and you can see whether you are getting the exactly enantiomer or not. Okay. Now let's say we'll start from the compared to the four group present here. So among the four group, which is the first priority? One, this is the two, this is the three, and this is the four. Okay. Now the four is the in x-axis, horizontal barabar. X-axis barabar. So that means 1 to positive rule and 1 to 3 clockwise. That means it is a R. Let's see. It is how it is looks like. So here also, which is the 1, carboxylic acid is the 2, CH3 is the 3, and hydrogen is the 4. Okay, now 1, 2, 3. The hydrogen is also again here it is a 4. So that means it is also positive rule, and here positive rule, and it is also 1, 2, 3. So that means it is a yes. So that means it is a, so this is a anti-clockwise 1, 2, 3 anti-clockwise. that means you are getting a S. So that means R in mirror image, it will show the, if R will mirror in mirror image, it will show the S, then it is a enantiomer. Okay. So two isomer of the lactic acid. So that's why they are saying the two isomer of the lactic acid, it is there. One is R or one is S. Okay. If they will ask in the other way around, how to project in other way around, like central gravity. This is a Newman projection and this is a Fisher projection. It's okay. But if you want to write in a the other way, that is a flying wedge rotation, flying wedge manner. So that means above, below, and plane. So let's say now let's see. Okay, here one OH is one, carboxylic acid is two. This is three. So one, two, three anti-clockwise. That means anti-clockwise four back. Four is the hydrogen, four back in positive rule. Always four back is the positive rule. That means it will show the S. This is a S molecule. Okay. Now you will see the R molecule. So if you see the how you will get the R molecule. So now from, if somebody will ask you from Fisher projection to write in a flying wedge manner, this is a Fisher projection. So if somebody asks you to write this Fisher projection to a this manner, then you have to write in this way, flying wedge, and the other molecule is the, this is the air. So how we will get the R molecule? So let's say one, okay, then this will be two will be carboxylic acid, two, three. So one, two, three. So if carboxylic acid is here and CH3 is here, then we will get the, so let's say here it is a carboxylic acid, here it is a CH3, here it is a OH, and here it is a hydrogen. Now you see one, two, three, four. So this is the clockwise. So this will be R. Okay. Now in this way, we are also getting in the flying wedge also. We are getting, what are the isomer we are getting? R as well as S. Both isomer we are getting here. So from you can see, so from the enantiomer, another most important point is that if you see any enantiomer, then there is a chance. There is a chance of you can easily consider that this is a R. If it is a R, so that means enantiomer. If it is enantiomer, so you will definitely get the S. If any molecule, if you see R and S, so they are enantiomer to each other. Okay. Now we'll go to the some example. What are the example we can? Maximum example we'll discuss so that there will be no such doubt. Even any doubt comes to your mind, you can ask me in between, or my contact number or my WhatsApp number or in my email ID also you can send me a question. Okay. Now, so let's say first we'll discuss this question, the molecule A. So the molecule A is A and B. They are isomer to enantiomer to each other. How? So as I told you, so let's say which is the, if you put any, if suppose you have a in your hand you have a molecule, and if you this molecule if you put in front of a mirror, then there will be a reflection. So what the reflection? So reflection, in this reflection, which is in the right side, it will go to the, after mirror image, you will see that in a right side mode, and if you see anywhere in the right side any molecule, any atom is present there, then you will see in a left side. Okay. Now the question is the A and B. Okay. So OH is the left side. So now you see after putting mirror here, let's say this is a mirror. Okay, let's say this is a mirror images. Now OH is in the left side. Now this OH in the right side. This hydrogen was in the left side, and this hydrogen now in the right side. Okay. and this hydrogen was in the right side, sorry, left side, sorry, this one is the right. So that's why it is coming in the left side. This is, sorry, this is the left, this is the right. So if it is the left, now it is coming in the right side, and here it is the left side, the bromine is coming in the right side. So CH3, this CH3 is same. But what are the thing it will change? The arm will be changed, because which is the more closer to each other, more closer to mirror, that will come first here. Then it will the molecule, the atom which is far away from mirror, it will also come. Sorry, in this way. So now you can see, so they are each other. They are actually they are mirror image of each other, non-superimposable mirror image of each other. So that's why you can say this is an enantiomer. We can also identify whether it is this carbon center and this carbon center. What is R and S? This is a one. This molecule, this carbon is two. This carbon is three. This is a four. Okay. So 1, 2, 2, 2, 3, 4. So clockwise. That means it is a R. Now you can see here 1, 2, 3, 4. So 1, 2, 2, 2, 3, 2, 4. So that means anticlockwise. That means IS. This R always give the S molecule. Now you understand that previous slide also I said that I told you that if you have a R and in the mirror image, if you are getting S molecule, then it is an enantiomer to each other. Okay, so this is the R. Now this is the S. Now let's say this will come. Will count this one. So 1. This is a 2. This is a 3. This is a 4. So 1, 2, 2, 2, 3 clockwise. That means it is also R. Now here count 1, 2, 3, 4. So 1, 2, 2, 2, 3 anticlockwise. This is also S. So that means RR and SS. So here we are also conclude that if you have RR and after mirror images, non-superimposable, if they are enantiomer to each other, then you will get the S and S. So RR is R always reflects to S molecule. Okay. Now these are the enantiomer. And in the case of C and D, so if you discuss the C and D molecule, so C and D molecule, how it is look like. So let's say this is also OH, this is OH, so this is a mirror image. Okay, now this OH is coming here, this bromine is coming here. Okay, now we'll discuss the stereochemistry. Let's say 1, 2, 3, hydrogen is 4. So clockwise, this is a R. Now 1, 2, 3, 4. So anticlockwise, that means S. This is R, this is S. Now bromine is here. So let's say 1, 2, 3, 4. So now 1, 1, 2, 2, 2, 3. This is also clockwise. This is also R. Okay, sorry. Anticlockwise. So 1, 2, 2, 2, 1, 2, 2, 3. Clockwise, anticlockwise. Anticlockwise. This is S. So this is R. This is S. Okay. Now let's see this one. So this will be 1. This will be 2. This will be 3. This will be 4. So 1, 2, 2, 2, 3. Clockwise. Clockwise. That means it will show the R. So this R molecule is showing S. R is showing S. And S is showing R. So RF is mirror images to SR. Okay. Now obviously the C and D are enantiomer. So this is also enantiomer. This is also enantiomer to each other. So this is also enantiomer. Enantiomer. This is also enantiomer. But there is a consequence. There people are always say one point in one line that two enantiomers are diastereomer to each other. So if they are, so A and C, because A is the what? A is the R and R. D is the S and Ace. C is the R and Ace. And D is the Ace R. Now A and B are enantiomers. C and D are enantiomers. But what about A and C, B and D? So then, so R to R not possible, but R to S is possible. So that means A, A and C diastereomer, so diastereomer, and B and D, B and D is the diastereomer. Why B and D is the diastereomer? So you can see D is the S and R. D is the SR, okay, and D is the SS. So maybe one R is enantiomer, but S to S is not enantiomer. So that means B and D are diastereomer. Diastereomer. Okay. So now you can also confirm that if these B and C or B and D, B and C or B and D are diastereomer to each other, or A and C and A and D diastereomer to each other. Okay. Now fine. Now we will we discuss the confirmation today or maybe the next week? Will we discuss? Hello, hello. Okay. So maybe so we have discussed so far. We have discussed about the here we have discussed three four question answer session, and then we have discussed stereoisomer. Then we have discussed the enantiomers. Then we have discussed enantiomer, diastereomer. Maybe then the next class we will discuss about the conformational and flying wedge and the Fisher projection and the Sohers projection and the planar symmetry. Okay, so these are the molecule left and the center of symmetry. These are the molecule left. Maybe the next class I will go through this one quickly. Okay, so that we can start. Okay, so maybe we'll stop here and maybe tomorrow we can start from the timing whatever we have. The 2 o'clock again I have another class. So tomorrow I will discuss about this flying wheel and the Fisher projection, all these things. So okay, see you next class.